All right, we're back. We're on page 121 of math analysis, and we are still talking about two-dimensional vectors. We just talked about component form, adding them, subtracting them. We looked at GeoGebra to see how we can move them around and make that happen. Now what we want to do is we want to try to talk about like multiplication, right? Addition, subtraction, we're good. Multiplication, does it exist? Well, here's a weird answer. There's kind of nothing that you would really call vector multiplication. On the other hand, there are three things that you might call vector multiplication, and therefore you don't call any of them that. So if you're curious what those three things are, the first one is going to be scalar multiplication, which we will talk about in a second. And then the other two will be, so the three things are: one, scalar multiplication. This is just for the people who are super curious. Two would be the dot product, which is like what? Sometimes called the inner product, I think. And then, no, I guess it would be, well, maybe it's called the scalar product. I think, I don't know. I don't use that. I don't use that name, so I can't even remember it. But dot product, and then the other would be called the cross product. We don't do cross products, partly because cross products don't really exist for two-dimensional vectors. All of them, however, feel like you are doing multiplication. In fact, the notations are kind of interesting, right? This one is going to be k times our vector, right, using multiplication. This one, you need two vectors. It's going to be a and then a dot b. That's like another notation for multiplication. And then the cross product takes two vectors and uses the x. So they actually use each of the three different forms of multiplication that we are used to. And they each do different things with vectors, because vectors are weird. Like, think about matrices. Matrices were weird. Like, matrix multiplication exists sometimes. Some matrices you can multiply, some you can't. Matrix division does not exist. So like, as soon as you meet a new mathematical construct type thing, you should start wondering, like, what can we do with it? Like with vectors, we've seen we can add them and we can subtract them. So that's nice. Now let's talk about scalar multiplication. So scalar multiplication is really similar to what you think of as multiplication for like real numbers, right? So if you had like 3 times 5, when you're first faced with that, you really just think it's like 5 plus 5 plus 5. And then if you had 5 times 3, you would think of it as 3 plus 3 plus 3 plus 3 plus 3. Like there are 5 threes. Scalar multiplication is the same thing for vectors. So what I want to do is I want to find 3v. And the way I find 3v is I just use v 3 times. So over here, I can see that v is the vector 4, 2. So since v is 4, 2, let's graph v 3 times. So I'm gonna, from this starting point here at 4, 2, I'm gonna go over 4 and up 2, which will take me here. Right, that uses v again. And then what I can do is I'm gonna duplicate it and do it again. And you can see how accurately I did that. So that should take me here. And this is the ordered pair 12, 6. This 3v, I don't really know where I'm going to do this. It should be like, oh wait, no, it's like totally here, right? Parallelogram or something. This is 3v's, so it's 3v. Let me see if let's see how much that matches up. Trying to pick you up and move you. Yeah, pretty perfect, except I didn't copy the arrowhead. So that's 3v. So 3v is just a vector that is 3 times the length of v. I'm actually just going to delete that because I don't really need it. But you can see that what I get is, so 3v is going to be 12, 6. You just use the vector v 3 times. And then if you look at it, you can do some weird stuff. So 3v is equal to, I don't know what manipulation I was hoping to do here. So I'm gonna say that this is 3 times 4 and 3 times 2, which is 3 times the vector 4, 2. So you literally just do 3 times each component. If it was 12V, I would do 12 times each component. The magnitudes are sort of interesting. So the magnitude of 3V, I mean, conceptually, there's no way this is anything other than 3 times the magnitude of V, right? We literally used V 3 times. So like, why would the magnitude of it be anything other than that? It wouldn't be. But I do want to show you a thing you can do here. So to find the magnitude or the norm or the length of this, I should do 12 squared plus 6 squared. So that was like a little long here. Let's see. So what you want to do is not go crazy. So I can factor this, right? It's 3 squared times 4 squared plus 3 squared times 2 squared. And then I can take out a 3, and I get 4 squared plus 2 squared. So I get 3 root. I mean, I could have taken out 2. I could take out another 2 squared, which is probably actually a better idea, but 3 root 20, which is 3 times the magnitude of V. And I know that it's the magnitude of V because radical of 4 squared plus 2 squared, and V is 4, 2. So that's definitely 3 times the magnitude of V. So the magnitude of 3V is 3 times the magnitude of V. So this says we could repeat the whole thing for U, or we could skip it since it's really not that complicated. I'll draw it. So let's say, what do we got here? 2, 3. So then I got to go another 2, 3. Well, 2, 3 times 3. So U is 2, 3. So 3U. 3U is going to be 6, 9. And then the 6, 9 fit on here? Yeah. Here. So let's draw this. And then here, this will be 3U. And it takes us, its component form is 6, 9. The magnitude of 3 times U is 3 times the magnitude of U. Like, it can't be anything else. So 3 is what's called a scalar. It's a real number. Later on in life, you'll have a function, a scalar function. Scalars can be positive, they can be negative. If the scalar is greater than 1, so like 5 times U, that'll give you a vector that is bigger than U, 5 times bigger than U. If the scalar is between 0 and 1, so like say 1/2, that's going to give you a vector that's shorter than the original, right? It scales it by a factor of 1/2. That's why it's called a scalar. So let's see if we can kind of summarize the possibility. You can also have a negative scalar. So a negative scalar does 2 things. It scales, right? So it either makes it bigger or smaller, depending on if the absolute value of the scalar is greater than 1 or less than 1. If the scalar is negative, it also switches direction. So we want to cover each of those possibilities. So let's say, let's see, let K element of the reals be a scalar. So can K be 0? I don't know. Well, I mean, it can be. And if it's 0, then we'll talk about that in a second. Like what happens? So let K be a scalar. All right. If K, let's say 0, K, 1. You get a shorter vector. Shorter vector, same direction. If K is greater than 1, you get a longer vector. Scaled it up, but same direction. Basically, if the absolute value of K is greater than 1, you always get a longer vector. And then the sign will tell you if you're going in the same direction or opposite direction, but whatever. So let's say, so how are we going to do this? -1, K, 0. You're going to get a shorter vector. And it's in the opposite direction. Opter, sure. And then if K is less than -1, you get a longer vector, so you scaled it up, but it's still, you switch the direction. opposite direction. Okay, if k is equal to 1, equal to positive 1, you didn't scale it at all. I mean, it's still a scalar, but you didn't scale it at all. If it's negative 1, you get exactly the same length, magnitude, or norm, but in opposite direction. So there's kind of a lot going on with that, but like it's not that bad. One thing that you do need to know is that like 0 times the vector 3, 5 is actually the vector 0, 0. This is called the 0 vector. So I mean 0 times any vector gives you the 0 vector, and the 0 vector is actually like a 0 with a line over it. So here, when we're looking at these, this right here isn't the number 0, it's the 0 vector, which is a vector that has as many components as you need. So if you have a 10-dimensional 0 vector, it's 10 zeros. If you have a 2-dimensional 0 vector, it's 2 zeros. It's as many components as you need so that you can still have a vector. So like when you add 2 vectors, you get a vector. When you subtract 2 vectors, you get a vector, which means sometimes you need to be able to get the 0 vector. And the reason for that is you don't want to run into a scenario where you have 3, 3 plus negative 3, negative 3. And you're just like, that's not a thing. It is a thing. What is it? It's 0, 0, the 0 vector. So adding and subtracting vectors needs to give you a vector. Scalar multiplication needs to give you a vector. So the output of any of those operations will be a vector. This is an important thing to keep in mind. Adding and subtracting gives a vector. Scalar multiplication gives a vector. Not everything you do to vectors will give you a vector back. So keep that in mind. And these are just like a million properties. I don't know, like none of them are really worth discussing. We kind of actually have looked at all of them. We got another 0 vector sighting here, right? Scalar multiplication always gives a vector. It's got to be a vector. Addition and subtraction always gives a vector. It's got to be a vector. This one is maybe the pickiest one. And I would say it's the pickiest because you actually get the absolute value of your scalar times the magnitude of the vector, which makes sense because magnitudes can't be negative. So if the scalar is negative, you just get the absolute value of the scalar times the length of the vector that you're scaling. So eventually, I'm sure almost all of you will at some point take a course called linear algebra, where you will learn a lot of these properties and you'll go into depth. And when I think back to that course, I think mostly of subscripts. I mean, I took theoretical linear algebra. I'm jealous. If you're going to take linear algebra now, you're probably going to, you'll be able to like watch the 3 blue, 1 brown video series on it, which you should definitely watch. You'll be able to play around with computers and look at things and like, I don't know. I'm jealous of anyone who gets to learn it now. So you'll take linear algebra, a lot of subscripts, just so many subscripts in that class. But anyway, I'll be back in the next video and we will do some more. So I will see you there.